Okay. The title of this presentation is Fabricator method based on synchrophasor voltage drop data for transmission backup protection. Okay, we're gonna see a long introduction. Then we're gonna speak about the actual methods used for wide area protection. Then the proposed advantage of the methodology. The advantage of the methodology proposed, an overview of the methodology, study case and conclusion. What I say that I gonna give you a long introduction, well, it's because I want to highlight the problems that we found in the power system, and also I want to clarify what is the goal of the methodology. Actually, the main goal is to identify the fault in a transmission system, electrical transmission system, using synchrophasor data. Okay. But what is a power system and what is a transmission system? Look, a power system is a group of electrical elements interconnected together in order to generate, transmit, and deliver energy to the consumers. Actually, the electrical power system, any electrical power system is too big. Is too big to be studied. It's too big. So most of the time when we want to make an analysis of the system, we split in three main parts: the generation part, the transmission part, and the distribution part. So the methodology that I'm presenting here is intended to be used on the transmission part, okay, the transmission system. The transmission system is also too long, and in order to make you see how long can be, we have here the map of the Mexican transmission system. In Mexico, we have three transmission systems. One is the central and south part, and also we have one isolated transmission system in Baja California, and one that is connected to USA through California. Okay. Due to the physical characteristics of the transmission system, is too exposed to failure conditions. A fault is a physical condition in electrical devices that cause maloperation. It can be a short circuit, open circuit, or intermittence. So what I am to do with the methodology? Identify a fault in the transmission system. Okay. Most of the time, here in the video we have how can a fault can occur. There are big trees nearby to the or near to the transmission lines that can touch one of the phases. The currents rise maybe 7 times more or 20 times more the steady state conditions. So the current becomes too high that can melt the cable. But no, this doesn't happen every time. No, we have some elements in here to protect the system, and what they do is isolate the part of the system that is on the fault, open a circuit breaker. But those elements can fail also, and sometimes they do not see the fault, so the fault evolve to a bigger problem, and instead of be only single phase, becomes three-phase fault and can damage any equipment nearby. The fault can be so severe or so intense that can produce a blackout, a cascade blackout. So we don't want that, no? We need to provide to the customer every time with the energy. And also we want to protect our transmission system, no? That's why we have relays. Relays are circuit breakers. The relays is an electronic numerical device that sends the electrical signals from the system and determine if the current and voltage are under the limits. If not, they send a signal to the circuit breaker to operate and open and isolate the part of the system that is on the fault. The primary protection function most of the time works properly. It's a very accuracy element. Maybe 99.98% of the time it works. During a fault, it works. However, uh, always we protect the system, every single element of the system, not only one time, but 2 times, and sometimes it's 3 times, because we want to make sure that we're gonna isolate the part of the system under fault. And the relays work very well. As I told you, 99.98% of the time they work. With this, we are speaking about classical system. Classical system that doesn't contain electronic devices. Okay, but nowadays, those classical systems are changing. Even in Mexico, we are connecting uh, green energy to the system. And those green energy are connected through voltage source converter, and voltage source converter are electronical devices that control voltage and currents as well, and limit the voltage and current. So the current don't gonna be 7 or 20 times more, it's gonna be at least two times more. This uh, make a really challenging to the relay. Actually, some of them becomes blind, so they might not operate during a fault. Okay. So why don't we look for another element to protect the system, not a relay, another element, and with another methodology, because we are doing the backup protection most of the time with the same element and with the same methodology, but with different sensitivities. Okay, so we are proposing here use the synchrophasor measurement unit. The synchrophasor measurement unit do two main tasks. It takes the electrical signals from the time electrical signals from the system and then transform the sinusoidal signals to a phasor signals. So first, we will have flat signals, horizontal flat signals during steady state condition and maybe during a fault as well. So this make it easier to detect a fault. But this is not the main advantage. The main advantage of a synchrophasor unit is that they can send and receive data from a satellite. They can send then the data that we collect through the system can send to a control room, and in a control room we can apply different methodologies and send it back to the breakers. Maybe for some of you this is so basic, but don't forget the speed and the dynamics that we have on the electrical power system. Talking about protection and faults, they can be a fault that lasts only microseconds, but they can be another transients, electromechanical transient, that lasts for 3 to 5 minutes. So the data must be sent to the satellite as fast as possible. A primary protection function works in 50 milliseconds, and a backup in 400 milliseconds, 600 milliseconds, etc. So now we know what a phasor measurement unit is. They collect all the phasors and then send to the control room. There are many proposed methodologies on the literature to protect. Sorry, before to start with this, I can say that here we can send the data from all around the system. No? If we have resources, enough resources, and speaking about computational elements, if we have all the resources, we can send all the data to the satellite and receive in a control room. There are other methodologies that have been proposed in the literature, but most of them present technical difficulties. Okay, they work very nice, but the time is not possible. The time to protect a system is not possible to use it. Among others, we have the iterative solutions like a trial and error, predictor corrector, nonlinear optimization techniques, and learning process. All of them are excellent techniques, but because the because the natural behavior of the methodologies, they take time, and the time that they take is more than the using protection. So that's why we cannot, some of them cannot be used on real elements. Okay, the methodology that we are protecting are split in three main extensions. That's why, because we want to decrease the computational burden. Because I'm speaking about data, but we sometimes don't understand how many data we have in the system. No? It's a lot of data. You already see the map of Mexico City. But this methodology we have implemented in real time and it works. That is a plus. Because if it was implemented in real time, that doesn't mean that can be implemented in a real element and can reach the necessary times. It's not necessary to have a measurement in all the buses of the system. We can look up some data. Also, it can deal with errors and make a power scene detection. We don't want to speak about power scene detection this time. And the data that we obtain, I already said that we want to identify the fault. So we want to identify the faulty area, the faulty line, the faulty circuit. I mean phase A to ground, or B to ground, C to ground, or between them, etc. This is the phase selection. We want to know the direction of the fault, and we want to know the distance of the fault from the nearest devices. Good. Okay, this is the methodology itself. We split it in three main stages, as I told you before. The first of them is done locally in the synchronous, in the phasor measurement unit. The phasor measurement unit is done. No. So we don't took so much computational resources. The next is done in the control room, and the third one is also done in the control room. What is about the first stage? Well, in the first stage, what we're gonna see is detect a fault, make the phase selection, and see the directionality. Because we are working with phasor data, we need to use new methodologies or the old methodologies with this data. So maybe we need to change the methodology that we use. As an example, for the detection, we use a modified delta current method where we compare the voltage during a steady state condition and the voltage during the fault. If there is a high difference between both measurements, and I'm talking about 10% of more because 10% is allowed in the system, then we're gonna send a pickup or an starting that there is a fault on the system. Okay. Then comparing the magnitude of the phasors, we will be able to see what type of fault it is. If the delta voltage, for example, from A is greater than the voltage from B and C, then we will have a A to ground fault, and it's the same for all the other elements. And the type, we determine the type with this formula, no? If it's a single phase to ground, two phase to ground, or three phase to ground fault. Okay, good. Then the directionality. Actually, we don't have here the directionality, but the directionality is computed by the angle between the voltage and currents. If the angle is less than 90 degrees, then we have a forward fault. If not, it's a backward fault. So with this idea, we can make a truth table and define if the fault is forward, is in on one area or not. For example, if we have a fault in area C, this PMU will see a fault backwards. This PMU will see a fault forward, and this PMU will see a fault backwards. So with this truth table, we want to define where the fault is. Then we go to the second step. And in the second step, we want to use the transmission lines the transmission line model, the equation of the transmission line, and we're gonna include some other elements in order to do over-determining matrix. So we use the impedance of the matrix and some of the currents measurements on the system. We also introduce some possible errors in the measurements of the voltage and currents. And we also include in this matrix the superimposed currents of the sending and receiving line. So we will obtain an overdetermined matrix that can be solved using the least square technique. That's why we say we can include the error on, and sometimes we don't need all the data. No? It's not necessary. Okay, so I obtain all the parameters in the matrix. Most of them are about the currents flowing through the lines. the real currents flowing through the lines. But this is not the solution that we want. We obtain the unknown values, and then we look for the residuals of the methodology, and the sum of all the vector of residuals will be noticeably small for a faulted line set of equations. We're gonna see in the example what I'm talking about. Okay. If the faulted line lasts at least 3 times, then we have a fault. If not, we're gonna send an alarm. Then at the end, we use this equation, including the propagation constants, to determine where the fault is in a single transmission line. Here we already know what is the transmission line and the fault, and here we determine the distance of the line. Okay, we implemented in a real-time simulator, as I told you. In a MATLAB software, we developed the control loop methodologies, and we include a delay, more or less the same that we might have with the satellite. And then we do this case of study. This is a system with 39 buses. It's a well-known system, that's why we use it. And we split it with 5 different PMUs and 5 areas. And we make a fault here. We detect the fault at this time. Then we make the phase selection at this time. Then we make the phase direction with the angles. Tómala. Sorry. This where we have the forward and reverse limits. With that, we determine the area under fault. Now we detect the area under fault, that is the area. What is the area? Faulty area 4, determined by 4. Then we have the residuals, and the residual from the faulty line is noticeable small. So it's really easy to determine the line under fault is the 414, and here we don't have the 39 lines. I think there are 48 lines, but we don't have all of them. We only have I think 10 lines. To compute, to the computational burden decrease a lot. And from here we determine the distance of the line, and at this time it was around at 8.59 kilometers. So we can send the crew to this place and see if and correct the fault, no, the damage. So as a conclusion, the methodology do the total identification of the fault by stage. In the first stage, they do fault detection, fault direction, and faulty phase detection. On the second stage, we determine the transmission line under fault, and in the third stage, we determine the distance from the nearby device. We do this, I think, 1,700 times to make that it works, and it works. Okay, this is all about my